NASA is about to launch a telescope that can photograph what Hubble would need 85 years to capture, and the first targets it has been assigned to study could rewrite the textbook on dark energy, dark matter, and whether Earth-like planets are common or extraordinarily rare. The Nancy Grace Roman Space Telescope is the most anticipated astronomical instrument since the James Webb Space Telescope, and in one critical dimension, it surpasses Webb entirely. Roman's wide field of view is approximately 100 times larger than Hubble's, while maintaining the same sharp resolution that made Hubble's images scientifically definitive. This is not a marginal improvement. It is a fundamental change in what a space telescope can accomplish in a single observation session. To understand why that field of view matters so profoundly, consider what Hubble's famous deep field images required. The original Hubble Deep Field, captured in December 1995, required 342 separate exposures accumulated over 10 consecutive days of observation time to photograph a patch of sky approximately 1/30th the diameter of the full moon. That tiny patch revealed approximately 3,000 previously unseen galaxies. Roman can photograph a region 100 times that size in a single pointing. What Hubble built across weeks of precious telescope time, Roman captures in hours. Roman's primary mirror measures 2.4 meters in diameter, identical in size to Hubble's mirror. The engineering achievement is not in the mirror size, but in the detector system behind it. Roman's focal plane array contains 18 infrared-sensitive detectors working in concert, covering a field of view of 0.28 square degrees, a number that sounds small until you understand that Hubble's field of view is 0.003 square degrees. The detector system is physically larger than any previously flown in a space telescope, and it operates in near-infrared wavelengths that pierce through dust clouds obscuring billions of stars and galaxies from visible light observation. The mission's 4 primary science objectives define exactly what Roman was engineered to answer. First, it will conduct the most comprehensive survey of dark energy ever attempted, mapping the distribution and clustering of hundreds of millions of galaxies across cosmic time to measure how the universe's expansion rate has changed. Dark energy constitutes approximately 68% of the total energy content of the universe, and scientists still fundamentally do not understand what it is. Roman is specifically optimized to constrain its properties with a precision no previous mission has approached. Second, Roman will map dark matter across an unprecedented volume of the universe using weak gravitational lensing, detecting the subtle distortions dark matter's gravity creates in the apparent shapes of background galaxies. These distortions are individually tiny, measured in fractions of a percent of a galaxy's ellipticity, but across hundreds of millions of galaxies, Roman's statistical power will produce the most detailed dark matter map in history. Third, Roman's microlensing survey of the central Milky Way galaxy is designed to discover thousands of exoplanets, including the first statistical census of free-floating planets, worlds that have been ejected from their star systems and drift through the galaxy alone. Current estimates suggest free-floating planets may outnumber stars in the Milky Way, but this has never been confirmed observationally. Roman's microlensing program will either confirm or challenge that estimate with real data. Fourth, Roman carries a coronagraph instrument, a technology demonstration device designed to directly image exoplanets orbiting nearby stars by blocking the overwhelming glare of the host star. This instrument is testing technology that will inform the design of future flagship missions specifically built to directly photograph Earth-like planets and analyze their atmospheres for biosignatures, the chemical fingerprints of life. The telescope is named after Dr. Nancy Grace Roman, who served as NASA's first chief of astronomy from 1959 to 1979. She made the critical administrative and scientific arguments that eventually led to Hubble's approval and development, fighting for decades to establish space-based astronomy as a legitimate and fundable scientific priority inside an agency primarily focused on human spaceflight. The telescope carrying her name will now operate from the same gravitational balance point as James Webb, the Sun-Earth L2 Lagrange point approximately 1.5 million kilometers from Earth, in a thermally stable environment ideal for infrared observation. Roman's current launch target is no earlier than May 2027, with hardware assembly and testing actively underway at NASA's Goddard Space Flight Center in Maryland as of 2025. The total mission cost is currently estimated at approximately $3.93 billion, a significant investment that reflects the scope of what the mission is designed to deliver across its planned 5-year primary mission, with the possibility of extended operations beyond that window. What makes Roman's arrival in astronomy genuinely transformative is not any single observation it will make. It is the volume of discovery it enables simultaneously. Every hour Roman operates, it is collecting data across a field of view large enough to contain millions of galaxies, thousands of stellar systems, and potentially hundreds of microlensing events. The data rate will be extraordinary, requiring new computational infrastructure and analysis pipelines to process the information it generates. Hubble showed humanity what the universe looks like, in exquisite detail at small scales. James Webb showed what the universe looks like in infrared, across cosmic distances. Roman is about to show humanity what the universe looks like at both scales, simultaneously, across the widest survey ever conducted from space. The universe has been patiently waiting to be mapped at this resolution and this scale. Roman is almost ready to begin. So tell me in the comments, if Roman's dark energy survey produces results that cannot be explained by any current model of physics and forces scientists to propose something entirely new to explain what is accelerating the universe's expansion, would that discovery change how you personally think about the nature of reality? Follow this page right now if astronomy genuinely moves you, because when Roman's first images arrive, we will be here to break down every discovery clearly and completely from the very first day.